Hello everyone, my name is Yael Zaffrani from the Biomedical Engineering Department at Technion, and I will present my work, qDWI-morph, Motion-compensated Quantitative Diffusion-Weighted MRI Analysis for fetal lung maturity assessment, which has been done in collaboration with Boston Children's Hospital with the support of the BSF. The normal fetal lung parenchyma development starts in the second trimester and progresses through multiple phases before becoming fully functional at full term. The first phase of development, the embryonic and pseudoglandular stage, is followed by the canalicular phase, which starts at 16 weeks. Then the saccular stage, which starts at 24 weeks, and ends with the alveolar stage, which begins at 36 weeks gestation. Newborns with inadequate neutral lung development are at risk for postnatal respiratory failure or even death. During week 16, intensive angiogenesis starts forming a dense capillary network, leading to increased pulmonary blood flow and perfusion. Hence, changes in the overall tissue diffusivity can serve as a functional indicator of lung development. So the big question is how to measure the overall tissue diffusivity in a non-invasive way. Diffusion-weighted MRI is a non-invasive imaging technique sensitive to the random movement of individual water molecules. The displacement of individual water molecules results in signal attenuation. This attenuation increases with the B-value, which is the degree of sensitization to diffusion of the MRI pulse sequence. The movement of water molecules depends on tissue microenvironments. Tissue with a restricted diffusion is brighter in the image. Typically, diffusion-weighted images are required at multiple B-values, and the signal decay rate parameters are quantified per voxel by least squares model fitting. According to the mono-exponential model, the signal of a particular voxel decreases exponentially with an increasing B-value, with a decay rate that depends on the overall diffusivity of the voxel. Call it the ADC, apparent diffusion coefficient. The ADC encapsulates both pure diffusion and perfusion influence on the diffusion-weighted signal. The clinical goal is to assess fetal lung maturation using quantitative diffusion-weighted MRI. The ADC is quantified per voxel by linear least squares regression to create an ADC map. Then, the averaged ADC in the lung can indicate the fetus's gestational age according to a saturation exponential model. Since the ADC quantification is done voxel-wise, it is sensitive to potential misalignment between images acquired at different B-values, which can occur from fetal motion. In the left graph, we see the expected exponential signal of a single voxel with an ADC of 2.5 times 10 to the minus 3. But the actual signal looks more like the right signal due to noise and fetal motion. And the predicted ADC is 3.5 times 10 to the minus 3. Previous techniques for motion compensation include image registration before fitting a signal decay model. The registration process aims to bring the volumes acquired at different B-values into the same physical coordinate space. However, each B-value image has a different contrast. As a result, independent registration of different B-value images may result in suboptimal registration, especially for high B-value images, where the signal is significantly attenuated and the SNR is low. Our goal is to enable a reliable, non-invasive assessment of fetal lung maturation by simultaneously estimating the qDWI parameters and the motion model. We define the simultaneous quantification and motion compensation problem as follows. We want to find the ADC and phi, the set of transformations that align the different B-value images to the model that minimizes the following equation, where B is the number of B-values used during the diffusion-weighted MRI acquisition. For each B-value, we want the motion-compensated image to be similar to the expected image according to the model. But we can optimize this equation directly. From an unsupervised deep neural network-based perspective, the optimization problem seeks to find the deep neural network weight, theta, that minimize the following, where the orange element is the first output of the network and represents the set of transformations phi, and the blue element is the second output of the network and represents the predicted ADC. The qDWI-morph model comprises two subnetworks, a model fitting subnetwork and an image registration subnetwork based on voxel morph. The input is a batch of 3D different B-value images from the same patient with their corresponding B-values. The output of our model is composed of the set of motion-corrected images forced pixel-wise to the mono-exponential model. Our method is iterative, where the motion-corrected images from the previous iteration enter as an input to the next iteration until convergence. We solve the optimization problem for each case separately, so no training process is involved. Our loss function consists of three terms: similarity loss, smoothness loss, and model fit quality loss. Minimizing loss similarity will encourage the images to be similar to the corresponding model images reconstructed by the model fitting layer. This loss alone may generate a non-smooth displacement field that is not physically realistic. Loss smooth encourage a smooth displacement field phi by regularizing the spatial gradients on displacement u. Loss model fit is the loss that is responsible for forcing each voxel to act according to the future mono-exponential model. This loss applied only on omega star, which is a subset of the image, including only voxels from the lung. By combining these three losses together, we introduce a biophysically informed loss. The data includes 38 cases with minor misalignment between the different B-values images. Each patient was scanned with 6 different B-values in axial and coronal planes. The B-values are 0, 50, 100, 200, 400, and 600 seconds per squared millimeter. The in-plane resolution was 2.5 mm by 2.5 mm, and the slice thickness was set at 3 mm. A region of interest, ROI, was manually drawn for each case in the right lung. We cropped each image to a shape of 96 by 96 by 16 and normalized it by the maximal value at the B equals 0 volume. Results. This figure demonstrates the average signal in the lung as a function of the B value. The left graph is the baseline, and the right is for the motion-compensated volume due to the qDWI-morph. The lines are the corresponding fit to the mono-exponential model. We can observe that after the motion compensation process, the dots behave according to the expected model and are less scattered. Here, we can see the correspondence of the motion-compensated volumes to the model volumes with three methods: baseline without motion compensation, qDWI-morph without fit loss, and qDWI-morph. Green and purple colors indicates a misalignment between the volumes and the model. Our method achieved better correspondence and is sharper than the method without the fit loss. This figure shows the ADC parameter plotted against gestational age for all three methods. The data is color-coded by the degree of conformity to the mono-exponential model in terms of R-squared. The darker the dot, the higher the R-squared. The baseline approach without motion compensation performed R-squared equals 0.13. Our method without the model fit loss achieved R-squared equals 0.28. And our approach achieved the best correlation with the ADC and the gestational age with R-squared equals 0.32. Summary. We introduced qDWI-morph, an unsupervised deep neural network approach for motion-compensated quantitative diffusion-weighted MRI analysis with application in fetal maturity assessment. Our model coupled a registration subnetwork with a model-fitting subnetwork to simultaneously estimate the motion between the different b-value images and the signal decay model parameters. The optimization of the model weight is driven by minimizing a biophysically informed loss representing both the registration loss and the fit quality loss. The proposed method can potentially improve our ability to quantify diffusion-weighted MRI images with motion. Thank you very much. Any questions?